Section 2.7, which is operations on convergent sequence. Operations on convergent sequence. So we have seen what is meant by a convergent sequence. So the theorem is that if sequence Sn and sequence Tn are sequences of real numbers, and if limit of sequence Sn is L and limit of sequence Tn is something real number m, then the limit of sequence Sn plus Tn is also L plus m. Right. So you might have idea about the limit of such thing. So by using the definition of limit of sequence, what is given? Sn and Tn are sequences of real numbers. Limit of sequence Sn is real number L. Limit of sequence Tn is real number m. Then limit of the sequence Sn plus Tn is L plus m. So what we wish to prove this thing, that means what? By the definition of limit of sequence, we wish to prove the result. What we should have? For given any epsilon greater than 0, we have to show that limit of this thing is L plus m. That means by the definition of limit, we must find a positive integer n such that the difference of Sn plus Tn minus L plus m, it should be less than epsilon for all n greater equal the positive integer n. Right? So now what is given? We have given that limit of sequence Sn is L. It means what? It means for any given epsilon greater than 0, there is positive integer, let us call it as n1, such that Sn minus L is less than some epsilon for all n greater equal this positive integer n1. And for the simplicity in this case, I will take epsilon to be epsilon by 2. Also, the second limit is given. The limit of sequence Tn is m. It means what? By the definition of limit, it means given any epsilon greater than 0, there is some positive integer, let us call it as n2, such that limit of Tn is m. Right? So again I will take epsilon by 2. It should be true for all n greater equal the positive integer n2. Right? So I will call it as equation 2. It has equation 3. And let me choose, if we choose this positive integer n to be maximum of two positive integers n1 and n2, then for any epsilon greater than 0, what we should have? 2 and 3 holds for all n greater equal n, right? If I choose n to be this maximum of n1 and n2, so Therefore, this difference Sn plus Tn minus L plus M will be less equal Sn minus L and Tn minus M. Right, so it will be definitely less than epsilon by 2 plus epsilon by 2, true for all n greater equal n, and which is epsilon. Therefore, this Sn plus Tn minus L plus M is less than epsilon for all n greater equal n. It means what? Limit of sequence Sn plus Tn is L plus M. Right? So the next theorem, if sequence Sn is sequence of real numbers, right? If C is any real number and if limit of sequence Sn is L, then limit of sequence C into Sn will be C into L. So I think it is not that much difficult result. Right? So let us prove this thing. Proof. So what happened to the equation if I choose C equal to 0? So then the result is true. Right? Now let me choose C to be non-zero. Now as it is given that limit of sequence Sn is L, it means what? By the definition, for any given epsilon greater than 0, there is positive integer n such that this difference Sn minus L is less than epsilon, and it is true for all n greater equal n. Right? So let me consider. Now consider this difference C into Sn minus C into L. So it will be modulus of C into modulus of Sn minus L. So definitely this thing will be less equal. Modulus of C into this thing is epsilon. So if I choose this epsilon to be epsilon upon mod C, so the thing will work for all n greater equal n, and definitely it is less than epsilon. Therefore C into Sn minus C into L is less than epsilon. It is true for all n greater equal n, and we can say that limit of C into Sn is C into L. The next theorem, if sequence Sn and sequence Tn are sequences of real numbers, and if limit of Sn is L and limit of sequence Tn is M, then limit of sequence Sn minus Tn is L minus M, and the proof is analogous to previous theorem. Right? We have shown that limit of Sn plus Tn is L plus M. So it is easy part. So let us go to next corollary. The corollary is that if Sn and Tn are sequences of real numbers, if each term Sn is less equal term Tn, and the limit of sequence Sn is L. Limit of sequence Tn is M. Then the limit L is also less equal M. So how to show? The very easy part. So since it is given Sn is less equal T, it means it implies that Tn minus Sn is greater equal 0. Right? Each term Tn minus Sn is greater equal 0. So now it becomes a sequence. Right? As Sn, Tn are sequences of real numbers, so Sn minus Tn or Tn minus Sn will also be a sequence. And each term Tn minus Sn is greater equal 0. So the sequence is sequence of non-negative terms. Right? Each term is either greater than 0 or equal to 0. Non-negative terms. Therefore, and we have seen the result that if every term of the sequence is non-negative, then its limit is also non-negative. Therefore, limit of Tn minus Sn will be definitely greater equal 0. And by previous theorem, what the theorem is, if Sn, Tn are sequences converging to L and limit L and M respectively, then the sequence Sn minus Tn has limit L minus M. So if this is the sequence and they are converging to M and L respectively, so their limits will be M minus L, right? And as this limit is greater equal 0, so it is the actual limit. M minus L greater equal 0. It is by this theorem. So what we get? L is less equal M. So the next theorem, the statement is that number 1, if 0 is less than x is less than 1, then sequence x raised to n converges to 0. Number 2, if x is greater than 1, then this sequence x raised to n diverges to infinity. So can you see, can you imagine the proof? So proof, let us suppose 0 less than x less than 1, then is it increasing sequence or decreasing sequence? It is decreasing sequence because for this interval 0 to 1, x raised to n is greater than x raised to n plus 1. It is true for all natural number n. So sequence x raised to n is decreasing or non-increasing sequence. Non-increasing sequence. Also, it is bounded. Why? Because x is strictly greater than 0 implies that x raised to n is strictly greater than 0 for all positive, and that means it is non-increasing sequence and bounded below, bounded by 0. So sequence x raised to n is bounded below. It means it is non-increasing sequence which is bounded below. Sequence x raised to n is non-increasing and bounded below. So what the result we have seen? So now let limit of sequence x raised to n is some real number L, and as we know, every subsequence of convergent sequence is convergent, since every subsequence of convergent sequence is non-increasing and bounded below, so it is convergent. Right? This is by theorem. As it is a convergent sequence, so every subsequence of convergent sequence is convergent. So as x raised to n is convergent sequence for this x 0 to 1 of convergent sequence x raised to n, so its every subsequence will be also convergent, is convergent, and it also converges to same limit L. We have seen the result, and has the same limit L. Therefore, the subsequence x raised to n plus 1 is convergent. Right? X raised to n plus 1 will be the subsequence of sequence x raised to n, will be convergent, and the limit will be also same as L. But it means what? X into limit of x raised to n will be L. That is, it means by our assumption, we have assumed that suppose it has limit L. So let us say only. So it is x into L equal to L. So this implies L into 1 minus x equal to 0. Since x lies between 0 and 1, so 1 minus x will not be 0. So L has to be 0, right? Therefore, the limit of sequence x raised to n will be 0. Therefore, if x lies between 0 and 1, then the sequence x raised to n is convergent, right? And it converges to the limit 0. Now, what about the second part? Second part is suppose x greater than 1, then what we can write? Then we can write x raised to n plus 1 to be x into x raised to n. And for x greater than 1, definitely this thing will be greater than x raised to n for any positive integer. So x raised to n is less than x raised to n plus 1 for all positive integer n. So sequence x raised to n is at least increasing or not decreasing, is non-decreasing sequence. Right? And we know that if sequence some sequence Sn is non-decreasing and not bounded above, then it diverges to infinity, right? So as we know, if sequence Sn is non-decreasing and not bounded, then it diverges to infinity, right? Therefore, it is enough to show What is enough? Now we have shown that it is non-increasing. It is enough to show it is not bounded above. So it is enough to show the sequence is not bounded above. So on contrary, suppose it is bounded above. As it is non-decreasing sequence and bounded above, so one theorem says that it should be convergent. A non-increasing sequence which is bounded below is also convergent. A non-decreasing sequence which is bounded above is also convergent. So by that result, so sequence x raised to n is convergent. So let us suppose, as it is convergent, suppose its limit is L. Then what happens to the case? So as it is convergent sequence, so every subsequence is also convergent and will converge to the same limit L, right? So every subsequence of convergent sequence x raised to n is also convergent, also converges to limit L, right? So therefore the subsequence x raised to n plus 1 of x raised to n is convergent and will converge to limit L. So therefore this thing can be written as is equal to L, but it means x into L equal to L, or L into 1 minus x is equal to 0. But since x is strictly greater than 1, so 1 minus x will not be 0, so L has to be 0, right? But as x is greater than 1, so every term of the sequence will be greater equal 0, and it is true for all positive integer n, right? So the limit will not be 0 because every term of the sequence is greater equal 1. So our assumption was wrong. It cannot converge to 0. As every term of the sequence is strictly greater than 0, so the sequence will not converge to 0, and it's a contradiction. Contradiction shows that x sequence x raised to n is not bounded above. Therefore, it diverges to infinity. So next thing is a lemma. If sequence Sn is a sequence of real numbers which converges to L, which converges to real number L, then the sequence Sn square will converge to the square of limit of the sequence Sn. Right? So in this proof, what we have to show? We have to prove that limit of sequence Sn square is L square. So how to prove this thing? How to prove this thing? So to prove this means we have to prove that, we have to prove that for given any epsilon greater than 0, we find a positive integer n such that Sn square minus L square is less than epsilon, and it is true for all n greater equal n. That means it is what? Modulus of Sn minus L into Sn plus L is less than epsilon for all n greater equal n. Right? So let me call it as equation 1. Now, suppose limit of sequence Sn is L as it is given. Every convergent sequence is bounded. We know the result. So as it is convergent to limit L, so the sequence Sn is bounded because we have seen that every convergent sequence is bounded. Therefore, given it is given that as it is convergent, it is bounded, so there is a positive real number m such that each term of the sequence is less equal m, and it is true for all positive integers n. So this thing, modulus of Sn plus L is less equal modulus of Sn plus modulus of L. That means m plus modulus of L, true for all positive integers n. So let me call it as equation 2. And also, as limit of Sn is L, so for any given epsilon greater than 0, we can have there is a positive integer n such that this difference Sn minus L is less than some epsilon for all n greater equal n. So let me call it as equation number 3. Right. So as it is m plus mod L, so let me choose this epsilon to be m plus modulus L. And now consider difference of Sn square and L square. So it is modulus Sn plus L and modulus Sn minus L. So by equation 2 and 3, this thing is less equal m plus modulus L, and this thing is less equal epsilon upon m plus modulus L for all n greater equal n, because equation 2 and 3 says it is true for all such n. Right, so it is equal to epsilon. Therefore, this difference is strictly less than epsilon for any epsilon greater than 0, and it is true for all positive integer n greater equal n. So we can say that limit of Sn square is L square. So it is assignment for you. The theorem: if sequence Sn and sequence Tn are sequences of real numbers, and if limit of sequence Sn is L, limit of sequence Tn is m, then limit of sequence Sn into Tn is L into m. So it is very easy part, and you can show this by using this previous theorem. So take it as a homework. And one more lemma is there for homework, because it is very easy to understand and write also. if sequence Tn is a sequence of real number, and if it converges to m, which is a non-zero real number, then limit of sequence 1 upon Tn will converge to 1 upon m. It is also a very easy part, and take this as also a homework.